In response to growing interest in the prevention of parametric rolling, we have published guidelines on preventive measures against parametric rolling. So in this presentation, I'd like to introduce our new guidelines. Here is what I'm going to talk about. In recent years, several accidents involving container cargo loss have happened due to parametric rolling. Parametric rolling occurs in head sea or following sea. Excessive rolling motion could result in the failure of the container securing system, but it is difficult to estimate maximum roll angle for container lashing calculations considering parametric rolling. Lashing calculations do not account for parametric rolling, so it must be avoided by appropriate operation. To reduce the risk of parametric rolling and ensure the safety of crews and cargoes, there are some measures. Operational guidance in the form of a pole chart is one of the effective tools to avoid the dangerous sea state where parametric rolling is likely to occur. Another approach is the equipment of anti-rolling tank to prevent excessive rolling motion. In order to support the installation and operation of these software or hardware tools, we published guidelines on preventive measures against parametric rolling in February this year. This guideline is intended to give a class notation for ships with a preventive measure and recommend a practical procedure for preparing operational guidance in the form of a pole chart. First, this slide shows a basic mechanism explanation on what is parametric rolling. This animation makes it easy to make sense of the phenomena of parametric rolling. Simply put, parametric rolling is a resonance phenomenon caused by periodic changes in the stability of a ship in a head sea, a following sea, or quartering sea. In the worst case scenario, heavy rolling, like over 20 or 25 degrees, can suddenly appear in just a couple of periods, and it is difficult to take any action once it happens. In general, parametric rolling is more likely to occur when the natural roll period is in the range of twice the encounter wave period. So it is important to estimate the ship natural roll period. And here, it should be noted that the current IS code formula for natural roll period should not be used for especially large vessels, as it is estimated too low. And you should pay due attention to the condition of swells, that wave direction is head and following sea, including range of plus minus about 6 degrees, and wave length is close to the ship length. Estimation of natural roll period is the most important for avoiding parametric rolling. This chart is the natural roll period is GM on the horizontal axis. GM is very critical factor for natural roll period. This is the result of assuming 14,000 TEU, 7,000 TEU, and feeder size container ships. You can see that the smaller the GM, the larger the natural roll period. If GM is small, the risk of parametric rolling increases. Generally, the roll angle would be larger for parametric rolling than synchronous rolling. This slide shows outlines of the guidelines. Functional requirements in Chapter 3 specify class notations according to various preventive measures such as anti-rolling device and operational guidance, including pole chart. A detailed technical background of parametric rolling is provided in the appendix of the guidelines. Especially Appendix 6 presents the practical procedure for preparing a polar chart based on the extended method of SGISC, proposed by Professor Umeda, who is a leading expert in the field of stability. SGISC means interim guidelines on the second generation intact stability criteria by IMO in 2020 for preventing dynamic stability failure mode, which are not covered by the existing intact stability code. This method can provide a polar chart for any shear state and any loading condition in a relatively low cost. Next, these are examples of class notation to a SIP with parametric roll preventive measures. For example, devices for reduction parametric rolling, such as anti-rolling tank, a fin stabilizer, a rudder roll, a stabilization control system, and operational guidance, polar chart, weather service, wave radar, and alert system with monitoring roll data. In this polar chart example, the radial direction is the SIP speed, and 0 degree is fixed at head C, and the counters are drawn at the maximum roll angle. Here are example of polar chart. This is the result of assuming 40,000 container ship using NK ship model. So it is clear that the larger the GM, the less parametric rolling risk there is. A smaller GM is more likely to cause parametric roll at a relatively lower wave height. And in our current situation, we can provide a polar chart for any shear state and any loading condition if requested. If we have half home data and ship data, across NK consulting service will do the calculation and provide a polar chart you requested. For future service to support operation, we are just trying to develop an API, application program interface, that can display a polar chart related to sea state information through data linkage with onboard navigation equipment and weather routing software. The API allows users to link a polar chart database prepared in advance with sea state and SIP information to display a polar chart based on actual condition. So, in response to growing interest in the prevention of parametric rolling, we will support the enhancement of SIP value by granting the class notation to SIPs. We have published guidelines to state the type of class notation and related requirement. We have developed a practical procedure for preparing polar chart that clearly indicate the risk for parametric rolling based on the extended method of SGISC, and can provide a polar chart if requested. And we are just planning on develop API that can link to the actual shear state and the SIP information in real time as our future service. Thank you for your kind attention.